All right, so today we are going to continue talking about finding side lengths of a right triangle, but there are times when we can get away from using the trig ratios, sine, cosine, and tangent. There are two special cases where there are nice, clean relationships between the side lengths that we can actually just use a quick pattern to come up with side lengths very, very quickly if we just know one. And not have to use the trig ratios. Those two special triangles are known as 45, 45, 90, 30, 60, 90 triangles. You heard these in geometry. We're going to bring those back now, right? The only difference is the way you may have been taught it in geometry. We're going to kind of skip over that and try to apply a little bit of a pattern to find these side lengths a little bit quicker. Okay, so for example, start with your 30, 60, 90 triangles first. One way to kind of remember and understand where the relationships of the side lengths come from. In a 30, 60, 90 triangle, we can actually create a 30, 60, 90 triangle by taking an equilateral triangle like this one. Equilateral, equiangular triangle, remember from geometry, all angles are 60 degrees, right? And for the purposes of this conversation, we're going to make all the side lengths 2, right? Now, if we were to drop an altitude, remember altitudes from geometry, it's that segment that goes from a vertex and is perpendicular to the opposite side. If we were to drop this altitude, then we will effectively cut this triangle in half, right? An altitude in an equilateral triangle is the same thing as a line of symmetry in a triangle, right? So we cut that in half. If we cut that in half, since the altitude is perpendicular, we'll create two right triangles. Okay? Now, what we can do is we can kind of pull that right triangle out from that equilateral triangle, right? So that you get this guy right here. And when you do that, we're going to bring side lengths over. So I'm going to bring measurements over. This 60 degrees would fit here. This side length of 2 would now be this. And then, since we're cutting this equilateral triangle in half, the side length here, that's 2, this whole side is 2, now it's going to get cut in half and make this a 1, so that we end up with a triangle that looks like this. Okay? This is your 30, 60, 90 triangle. Now, we don't have the length of this leg right here that comes from the equilateral triangle. So what we could do is do quick Pythagorean theorem, right? 2 squared equals 1 squared plus x squared. This is 4, this is 1. Subtract 1, you get 3, square root, and this ends up being the square root of 3. Okay? And what we did in geometry was we used the idea of similar triangles and setting up proportions. Geometry was all about setting up proportions sometimes. And so what we talked about was that every 30, 60, 90 triangle, no matter how big or how small, were similar. And if they're similar, we can write a proportion between their sides. So say, for example, we had a 30, 60, 90 triangle here. And let's say that the hypotenuse here was 20. Then what we did was we matched up this bigger triangle with this base triangle down here of a side length 1, 2, and radical 3. And we said, okay, write a ratio of hypotenuse to hypotenuse, right? So 20 to 2. And then say we want to find this leg right here. We wrote a ratio of that leg to the corresponding one in the base triangle. And so you got that proportion. You cross-multiplied and got the side length, and everything was fine, right? Well, I want to use the idea of, instead of similar triangles, just understand that in this base triangle, it's telling us something. It's telling us that the hypotenuse is going to be twice as long as this leg. And this leg is going to be radical 3 times longer than that leg. So what does that mean? That means that however long this leg is, and I'm going to stop calling it this leg and call it the short leg. Why is it the short leg? Well, because 1 is less than radical 3. Where is the short leg always located? It's always located across from a 30-degree angle. Okay? So anyway, back to the relationship. All I do is I take the short leg and I multiply by 2 to get the hypotenuse and multiply by radical 3 to get the long leg. And if I need to work backwards, I just divide. Divide by 2 or divide by radical 3. Okay? This can be very much, can be a lot faster and a bit easier to get to our side lengths. So let's try to apply the relationship and see if we can't get these side lengths a little bit quicker. Okay, the idea that the hypotenuse is twice as long and the long leg is radical 3 times, right? So for example, this guy here. One thing to understand is that the relationships, you know, the hypotenuse being twice as long and the long leg being radical 3 times as long, all hinges on knowing the short leg. So if you don't know the short leg, if you haven't been given the short leg, you've got to find that one immediately, okay? So here we are. We look, and we're given the short leg. And I know it's a short leg because it's across from a 30-degree angle. Since the short leg is 5, that means the hypotenuse is going to be twice as long with that times 2. So the hypotenuse is going to be 10. Okay? The long leg is radical 3. So this times radical 3, which means we just apply a radical 3 to it, 5 radical 3. And that's it. We've got our 2 side lengths. We didn't have to do proportion. We didn't have to do sine, cosine, tangent. Bam, it's done. Okay? Same thing here. Now we've been given the hypotenuse. If the hypotenuse is 24, it's supposed to be twice as long as the short leg, which means if I want to find the short leg, instead of multiplying by 2, go opposite and divide by 2 and make this guy 12. Remember, the short leg is always across from a 30-degree angle. Well, if the short leg is 12, then all I do is multiply radical 3 to find the long leg and make this 12 radical 3. And we're done. Okay? It can be that quick and easy. Now, the only time where you have to think a little bit harder and a little bit longer is here, where we're given the long leg. Now, I'm supposed to short leg times radical 3 to get to the long leg. In order to go from long leg to short leg, I have to pull a radical 3 out of that. I got to divide by radical 3. Okay? But remember, we got to rationalize. So we take radical 3 to the numerator, 3 stays in the denominator, and then we can divide those guys out and go 4 radical 3. Or said another way, since radical 3 is in the denominator, how this ends up working out is just divide 12 by 3 and then put a radical 3 on it. So you get 4 radical 3. Okay, and that will work every time too. Now that we have the short leg of 4 radical 3, I multiply it by 2 or double it to get the hypotenuse, and that's just a matter of multiplying the coefficient by 2 or doubling the coefficient and getting 8 radical 3. Okay? All right, a few more here. So we try this one. Think about it for a second, and you can even pause the video, write it out, and then see if you're right. Okay, so this is the long leg. Since we've been given the long leg, we needed to divide by radical 3 to get to the short leg, or pull a radical 3 out. Nice thing is the radical 3's divide out. We get 8 for the short leg, and then we just double it to get the hypotenuse, which is 16. And we're done. Okay? All right, so that's our 30, 60, 90. The same can be done with our 45, 45, 90. We started with a base in geometry. We started with a base triangle, created some proportions, and set up those guys to find our missing sides in any other 45, 45, 90 triangle, right? No matter how big or how small, the relationship will still be the same. But there's a pattern to be had here as well. Now, there's nothing fancy like pulling, you know, this triangle out of an equilateral triangle or anything. But the pattern still exists. We can use what we know about a 45, 45, 90 triangle, which is if these angles are the same from geometry, that means that the opposite sides have to be the same. This is a nice isosceles right triangle. So the legs are going to be the same length. Okay? We can make them the same, both 1 if we want to, and then do Pythagorean theorem. And if we do, we get to this base triangle right here, which is 1, 1, and then radical 2 for the hypotenuse. What that tells us is that the legs are the same, and the hypotenuse is radical 2 times the leg. Okay? And we can use that idea as well. Okay? Now, we do have to kind of, and I'll go back, we have to sort of keep in mind the relationship between, the differences between 3690 and 454590. And I like this pulling a 30-60-90 out of an equilateral triangle because it helps keep those relationships straight. In a 30-60-90 triangle, you're going to have three different lengths, right? Three different side lengths. You're going to have three different angle measures, so that makes sense. But because we're pulling this from an equilateral triangle of side 2, then that means that our hypotenuse is 2, and we're taking half of that, so that's where our short leg is 1. Okay? But anyway, it's within a 30-60-90 that the hypotenuse is twice as long, and we use radical 3 in 30-60-90 because there are three different angle measures, 30, 60, and 90. So radical 3 gets applied to a 30-60-90 triangle versus a 45-45-90 where it has a radical 2 in it in the relationships. And since 45-45-90, there's only two different numbers for angles, 45 and 90, that maybe that's a way to remember that we use radical 2 in that relationship. Okay? So anyway, however you want to remember it, but you've got to memorize the relationships between these two sides of the 45-45-90 and 30-60-90 triangles, or the three sides. Okay? So back to 45-45-90, the legs are the same and the hypotenuse is times radical 2. Okay? Here we've got a 45-45-90 triangle. How do we know? Well, these angles have been marked congruent. Those are your acute angles of a right triangle. They have to add to 90. So if they have to add to 90 and be the same, then we cut them in half. Then we have to, split them up evenly, 45 and 45, which makes 90. All right, so anyway, 45-45-90 triangle, which means that if this leg is 5, that means y has to be 5 automatically, no problem. And then if I want to find the hypotenuse, I just multiply by radical 2 or make it 5 radical 2. Okay, and that's it. We're done. A little bit quicker. Another 45-45-90 triangle because the angles have been marked congruent. If this leg is 3, then that means x has to be 3 automatically. And then how do you get the hypotenuse? Just apply your radical 2 to it. So 3 radical 2. Okay? This guy is a little bit different. The hypotenuse is 10. Now, to get the hypotenuse, we have to multiply by radical 2. But I already have the hypotenuse. I have to go backwards, which means I have to divide by radical 2. But to rationalize, bring your radical 2 up, leave 2 in the denominator. You can divide those guys out, and you just get 5 radical 2. So this leg is 5 radical 2, which means that this leg is 5 radical 2. And that's it. Right? Try this one. Think about it for a second. You can even stop the video and then bring it back up to check to see that you're right with what you're thinking. All right. So again, we know the hypotenuse. So to go back to the leg, we have to divide by radical 2. We've got to pull the radical 2 out. Well, those divide out, which means that this is 5. This is going to be 5. Okay? All right. Well, let's put these all together. We've got a couple of diagrams here of a couple of different special triangles in it. Work your way into A, B, C, and D. Again, you can stop the video. And then when you start it back up, I'll walk through it. Okay, you got it? Well, here we're at 24, so we got to work from this guy. This left-hand triangle is a 30, 60, 90. That's the hypotenuse. Since the hypotenuse is 24, that means the short leg, which has to be this guy, is 12 because it's across from the 30-degree angle. Well, the short leg is 12. Then I apply a radical 3 to get D, because remember, a 30, 60, 90 has a radical 3 in it, in the relationship. Okay? Now I move over to the right triangle, and it's a 45-45-90, so these guys are the same. So B is 12 radical 3. And then to get C, to get the hypotenuse of a 45-45-90, you've got to multiply by a radical 2. Well, to do that, just multiply the 3 and the 2, you get 12 radical 6. Okay? You've got another one to try. So go ahead, stop the video, work it out. and then bring it back, start the video back up and check your work. All right, so again, 30, 60, 90 right here. So since the hypotenuse is 9, I got to take half of it. I got to divide it by 2 to get the short leg. So 4.5. And then just tack on a radical 3 to get the long leg, 4.5 radical 3. Okay, all right, no problem. On the right-hand triangle for W and Z, the 4.5 is the long leg. So I've got to divide it by radical 3 to get to the short leg. Rationalize it, get you 4.5 radical 3 over 3, which you can actually divide the 4.5 and the 3 out and get 1.5 radical 3. So Z is 1.5 radical 3. And then that's the short leg. To get the hypotenuse, we want to double the short leg. So just double 1.5 or 1.5 and you get 3. You get 3 radical 3. Okay? Hopefully that makes sense. Keep trying to apply these shortcuts. If it takes a little bit longer for it to click, that's okay. I think that eventually it will, and it'll make your life a little bit easier when you can recognize these special right triangles. Okay? Now, last thing I want to get to with you is the idea of all of these trig ratios for our special right triangles. We didn't do this in geometry, but this is going to help set us up for our unit circle stuff that we're going to do later. And what's interesting is it also allows us to review the fact that the trig ratios are comparing side lengths. So for any given angle measure, the trig ratio will always reduce to be the same, no matter how big or how small that right triangle might be. In other words, if I've got a 30, 60, 90 triangle, whether it's on this page or as big as a house, it doesn't matter. When I look at the ratio of sine, say, if I compare the opposite side to the length of the hypotenuse, it should reduce down to the same thing every time. And that is what I get if I go back to the basic 30, 60, 90, which is the 1 for the short leg, 2 for the hypotenuse, and radical 3 for the long leg. Now, if we go to 60 degrees and write the ratio of sine, it's going to be the square root of 3 over 2. And I don't care how big the triangle is, how long those sides are, if it's a 30, 60, 90 triangle, then the sine will always be radical 3 over 2. Always. Cosine of 60 will always be a half. I don't care how big or how small the triangle is. The ratio will reduce to 1/2. Tangent of 60 will always be the square root of 3. Opposite over adjacent here. Cosecant of 60 will always be, flip this over and then rationalize, we get 2 radical 3 over 3. Secant of 60 will always be 2 if we flip over the cosine of 60. Cotangent of 60 will always be 1 over radical 3, and then we rationalize radical 3 over 3. Always, always, always. This is always going to be true. It's a little bit of foreshadowing into our unit circle. Okay? And then lastly, the same thing can be done with our 45, 45, 90 triangle. If we go back to our original, that tells us what the ratio of these 6 trig ratios will always reduce down to. Sine of 45 will always reduce down to 1 over square root of 2, or after you rationalize, radical 2 over 2. Cosine of 45 will also always be 1 over radical 2, or rationalize to radical 2 over 2. Tangent of 45 will always be 1, because the opposite and adjacent will always be the same. Right? And then our 3 new ones. Cosecant of 45 will always be radical 2 if you just flip over sine. Secant of 45 will always be radical 2 if you just flip over cosine. And cotangent of 45 will always be 1. I don't care how big or small that right triangle is. As long as it's a 45, 45, 90, those will always be the values of those trig ratios. Okay? All right. So take those ideas and these shortcuts and apply them to your homework that's sitting out in Canvas, and we'll go over that next time.